We're continuing with Chapter 5 in the statistics textbook. In this video, we're going to go through the last section, which is on change of scale. Okay, so we saw in Chapter 4, when we were working the example problems, in the example problem video in the computing the standard deviation section, there was a series of 3 problems that the book gave. And what we learned was that if you add the same number to every entry in a list. Let's just assume that number that you're adding it could be a positive or negative number. You add the same number, like you add 5 to every entry in a list, or you subtract 3 from every entry in a list. It's the same number. You can't switch. You can't add 3 to one entry and then subtract 5 in another entry. You do the same thing to every single entry in the list. Then if you compare the average and the standard deviation of the list before and after, then the average has been changed by the same amount that you added or subtracted to each number. So if you added 5 to each number, then the average has increased by 5. If you subtracted 3 from each number, then the average has decreased by 3. And then the standard deviation didn't change. So in effect, all you're doing is you start here and you're just shifting the histogram left or right. I'm drawing like a normal distribution, but it doesn't have to be normal. It could be any distribution. Even if you had, a tail, then if you added or subtracted that same number, you would just shift this to the right or to the left. We also learned that if you multiply each value in a list of numbers by the same number, and let's just for the moment assume that the number you're multiplying by is a positive number, then the average, when you compare the averages and the standard deviations before and after, the average gets multiplied by that number, and so does the standard deviation. So if you multiply every number in the list by 3 and you compare the average and standard deviation before and after, you'll see both the average and the standard deviation were multiplied by 3. Okay, now if you multiply every number in the list by -1, then the average gets multiplied by -1. The standard deviation doesn't change. And the way you think about that is, so if you have a histogram like this, then what's happening is this is the average. Let's say the average is 20. Then the average changes to -20 and the whole histogram flips. Right? Even the tail flips. But the standard deviation still doesn't change. It's still the same standard deviation, right? And so you can also think about, like, let's say you multiplied every number in a list by -3. Then what would happen? You would multiply the average by -3 and multiply the standard deviation by +3. You don't apply the -1 to the standard deviation. So now with that, you can think about, you could do any kind of combination of, you start with a list of numbers and I could say, okay, I'm going to start with this list of numbers and I'm going to multiply every number by 3 and add 6. Or vice versa. I could add 6 first and multiply by 3. And so any operation that you do, you start with a list of numbers and you either add the same number to each value in the list, add or subtract, multiply, and you could also include minus signs when multiplying, or any combination of all of that. That's called a change of scale to that data. You change the scale. Okay? All right, so now let's go through this section and you'll get a better sense of what exactly that means. Okay, so it just starts off by stating everything that I just talked about. If you add the same number to every entry on a list, that number just gets added to the average. The standard deviation does not change. The deviations from the average do not change because the added constant just cancels. Furthermore, if you multiply every entry on a list by the same number, the average and the standard deviation simply get multiplied by that number. There is one exception. If that constant multiplier is negative, wipe out its sign before applying it to the standard deviation. Okay, so what we're going to do here is, let's look at this a little bit deeper. In particular, we're going to look at how applying these kinds of operations affects the standard units. So, all right, find the average and standard deviation of this list, then take this list, multiply each entry by 3, and then add 7 to to get this new list, and then find the average and standard deviation of this new list. Okay, so each of these operations here, it's everything we talked about. It's a combination of multiplying every number in the list by the same number, as well as adding every number in the list by the same number. And so if we find the average and standard deviation of this list, and then find the average and standard deviation of this list, based on everything we just talked about, we know what's going to be the difference between those two. So first, you're going to take this average and multiply it by 3. And you're going to take this standard deviation and multiply it by 3. Then the next step is that new average and standard deviation. When you add 7 to each number in the list, you're going to add 7 to the average and not change the standard deviation. So let's see if that's what happens. All right, the average here they're saying is 4. And the standard deviation is 2. So after this first step, when we multiply each entry by 3, but we haven't added 7 yet, we're going to get a new list. That new list is going to have an average of 12 and a standard deviation of 6. Okay, and then after that, when we add 7, then what's going to happen? The average will go from 12, and you'll add 7, so that's 19, and the standard deviation won't change from 6. So this second list here should have a average of 19 and a standard deviation of 6. And that's what, there you go, see? Okay, but now what they want to do is, here's the same two lists, but let's convert them to standard units first. All right, so if you convert the first list to standard units, you get this. And if you convert the second list to standard units, you get that same exact list. So that's interesting, right? If we did any kind of combination of adding the same number to every number in a list, subtracting the same number, multiplying the same number, any combination of that, then as far as the standard units go, the standard units don't change. The list of standard units, not like, we're not just talking about the average or the standard deviation or something like that. If you have a list of numbers and you convert that list of numbers to standard units, so you have a parallel list, okay, then you go back to the original list and you do any kind of combination of adding the same number, multiplying the same number, adding and then multiplying, whatever, and you get a new list. It could be no matter what. You could add something and then subtract something, then multiply the same number, then after that, add again, and you could do anything you want. You get this other list, and you convert it to standard units. Those two standard units lists are going to be exactly the same, unchanged. Now, there is one exception in the sense that, notice how what we did here, we didn't multiply by a negative number. If you multiply by -1 or any negative constant, then it will change the standard units list. It'll if we multiply by -7, let's say we added 3, or no, we multiplied each entry by -3 and then added 7. Let's say we did that. Then if you compared these two lists, this list, the final list would be every entry will be multiplied by -1. That's the only difference. Now, if you multiply by -3, then added 7, and then multiplied by -5, then you would get the same standard units list at the end, because you first multiplied this list by -1, and then you multiply by -1 again, so you get the same list back. But still, though, in general, you can see that you're not changing the standard units for the most part. If you do any one of these adding, multiplying operations, which are called changes of scale. List B comes from list A by changing the scale, multiplying by 3, add 7. The 7 washes out when computing the deviations from average. The 3 washes out when dividing by the standard deviation, because the standard deviation got multiplied by 3 along with all the deviations. That is why the lists are the same in standard units. To summarize, adding the same number to every entry on a list adds that constant to the average. The standard deviation does not change. Multiplying every entry on a list by the same positive number multiplies the average and the standard deviation by that constant. But if it's a negative number, then you do the same thing, but just don't multiply the standard deviation by -1, or leave the minus sign out of the multiplier for the standard deviation. These changes of scale do not change the standard units, but it's going to mention here, if you multiply all numbers on a list by the same negative constant, in standard units, that just reverses all the signs. All right, so why is this called? Why are these called changes of scale? Where does this name come from? And they give an example here of if you're converting from degrees Fahrenheit to degrees Celsius. Imagine you have a list of temperatures, a list of numbers, there are a list of temperatures in degrees Fahrenheit, and you want to convert all of those to degrees Celsius. Well, when you do a conversion like that, it's not like you do different things to different entries, right? That doesn't make sense. You do the same conversion operation to every single entry. And conversion factors, whenever you convert units, conversion factors, it's going to be sometimes you're just adding the same, like if you're going from Kelvin or Celsius to Kelvin, all you're doing is adding 273. Or no, if you're going from Celsius to Kelvin, you just add 273 to each value. That would be a change of scale. Or like shown here, you actually, you multiply everything by a constant as well as subtract something from every entry. So it's like a combination of both of those. But anytime you're changing units, it's going to be some combination of like multiplying and adding or something like that. But what they're trying to illustrate, though, is that, so yes, if you had a list of temperatures in degrees Fahrenheit and you made a histogram, and the horizontal axis is not in standard units, it's in degrees Fahrenheit, and then you changed to, you converted to degrees Celsius, you're going to get a different histogram, of course. And we know how the histogram is going to be different. It's going to be shifted to the left. The average is going to be 32 units less. And then from there, the average and the standard deviation are going to be multiplied by 5/9. That's how it's going to look different. But in standard units, we know that we're not multiplying by any negatives, so the standard units aren't going to change. So what's that trying to illustrate? The idea is, so those numbers, they start in degrees Fahrenheit, they represent some, temperature distribution or something. Just because you change scale, just because you change units, it's still the same temperature. Like the actual physical nature of what's going on is the exact same thing. It's not like you've changed the heat content of whatever those temperatures are talking about. And so that's the idea. That's what they're calling it, a change of scale, and that's what they're wanting you to think about the standard units as. Just because you change the scale, there's something fundamental underneath that doesn't change, and that's the standard units. Other than, yes, if you multiply by a negative, you're going to flip the sign. You're going to flip the signs of every entry. But still, even in that case, the fabric of the standard units is the same. Okay, now let's work this problem here. A group of people have an average temperature of 98.6 degrees Fahrenheit with a standard deviation of 0.3 degrees. Translate these results into degrees Celsius. All right, so the average in degrees Celsius, we just convert 98.6 and use this conversion factor here. Convert 98.6 degrees Fahrenheit to degrees Celsius. So minus 32. All right, so 37 degrees Celsius. Okay. Now, this is a little bit different here. You might think, well, okay, let's just do 0.3 degrees Celsius conversion, but we're really, this is in degrees Celsius, because remember, we talked about how the units of standard deviation are going to be the same units as the units of the list of numbers, but the difference is it's a change in degrees Celsius. So it's not a different unit, but the conversion factor is different is all. So we need what's the conversion factor for a delta degrees Celsius? Well, if you imagine you have like a F1, F degrees Fahrenheit 1 and an F2, then you do, so 5/9 F1 minus 5/9 times 32. Well, okay, no, we would do F2. We'd start with the second one. 5/9 F2, and then minus 5/9 F1 minus 5/9 times 32. and then these go away. Like, so what you end up getting is 5/9 and then delta F. Delta C is just 5/9 delta F. So this is the delta F, right? 0.3 degrees. So we don't add the 32 or subtract the 32 is all. So again, it's still degrees Fahrenheit and degrees Celsius. It's just the conversion factor is different when you have a change like that. Sometimes it is, sometimes it isn't, depends. So we just do 5/9 times 0.3, 0.17. So this is 0.17 degrees Fahrenheit. All right. Someone's temperature is 1.5 standard deviations above average on the Fahrenheit scale. Convert this temperature to standard units for an investigator who is using the Celsius scale. Okay, now you might be tempted to say that, all right, well, we're going to multiply this by 5/9, but remember, it's not the actual standard deviation. This is standard units. It's like how many standard deviations. And remember, the standard units don't change unless there's a -1 and there's a minus sign. There's no minus sign in here being multiplied. So this isn't going to change. And as far as if you're going from the Fahrenheit scale to the Celsius scale with this conversion factor, the standard units aren't going to change. So it's going to be 1.5 standard deviations as well, Fahrenheit or Celsius scale.